Hello everyone, welcome to Physics Pathfinder. Today we are going to cover the topic B3, which includes gas laws. So in today's session on gas laws, we would be investigating different gas laws. We would be seeing the equation of state for an ideal gas, work few exam style questions, and also do kinetic theory of ideal gas. So let's start today. What is gas pressure or what is a pressure? Pressure, as we know, is defined as force applied per unit area of any object. When you apply a force perpendicular to the area of cross-section, then that force applied in that area is called as pressure, which is measured in pascals or Newton per meter square. Then what causes gas pressure? As you can see in the animation here, the gas molecules are continuously in random motion. As they are moving around in a very high speed, they strike against the walls of the container and they also hit among themselves. When they strike against the walls of the container, there is a change in momentum associated with these gas molecules. So that change in momentum that happens per unit time or rate of change of momentum, as we know, is called as force. Rate of change of momentum of the gas molecules as they hit on the sides of the container of the gas. So there is a force applied on the sides of the container or walls of the container because of change in momentum associated with the gas molecules. And this force applied per unit cross-sectional area of the sides of the container is what is gas pressure. So just by hitting on the sides of the container is what causes the gas pressure. Now, when we investigate any gas, we have four parameters that we need to investigate. It's pressure, volume, temperature, and mass. At a time, we investigate change in one quantity. How does it affect on the other quantity? So one is a dependent variable and one is the independent, and the other two is a control variable. So take an example here. If I am investigating pressure versus volume, how does a change in pressure affect the volume, or how does the change in volume affect the pressure? Where the other two quantities, that is temperature and mass, is a constant. And this is nothing but our Boyle's law. The next investigation could be pressure versus temperature, where volume and mass is fixed. How does change in pressure affect the temperature or vice versa, which is a Gay-Lussac law. And the same thing, how does the change in volume affect the temperature, where you have pressure and mass constant is called as Charles law. So these are the gas laws where we investigate change in one, how does it affect the other, and the rest two parameters are a constant. Let's see some questions here. Read carefully, try to guess the answer, and then come back for the results. So if you can see here, an ideal gas of constant mass is heated in a container at a constant volume. So we can see there are two constants here, mass and volume. So you are only investigating pressure and temperature. What is the reason for the increase in the pressure of the gas? What causes the increase in the pressure of the gas? And the answer could be average force per impact on the sides of the container wall. If it increases, means pressure is increasing. If pressure is increasing, means temperature will also increase. So the answer is B. Next question. A substance in gas state has a density 1,000 times less as compared to its density in liquid state. The diameter of the molecule is d. What is the best estimate of the average distance between molecules in a gaseous state? So we know that density in the gaseous state is 1/1000th time density in the liquid state. So if density is 1/1000, we can tell that volume is inversely proportional. So volume is 1000. 1000 times the diameter of the volume is 1000. Volume is nothing but this distance cube. So if I take the distance as x cube is 1000, what will be the distance? Cube root of 1000, which is 10. So the distance between the average distance between the molecules in the gaseous state is 10 times the diameter of the molecule, which is B. Next, you have given too many compounds and they're asking you which has the greatest number of molecules. Greatest number of molecule is when you have to just count. It's very simple. Here we have 3, 3, 3, but here we have 5. So the answer is D. Next, let's study about Avogadro's constant. What is an Avogadro's constant? If I take 12 grams of carbon or 31 grams of phosphorus, each of them have a constant number of molecules, which is called as the Avogadro's constant. So the number of molecules in 1 mole of a substance is called as the Avogadro's constant. Should be in the data booklet. We can note down this value 6.02 into 10 to the power 23. These many molecules are present in 1 mole of any substance. Now we'll see the relation between the number of moles, the number of atoms, and Avogadro's constant. So the ratio of number of atoms over the Avogadro number gives you small n, which is number of moles. Let's do one exam style question. Look at this. There is a thin walled cylinder having a weight W. So the force acting downwards is weight, which is mg. It rests on a flat surface. The cylinder has a radius r, the height is L, and the average thickness is x, where r is much greater than x. So while calculating, we have to take care that the measurements of r related to r is much, much greater than x. That is, anything related to x squared can be neglected. This is the hint. So you can see here, to get the radius, to get the area, we need to first find pressure. Pressure, as you know, is force exerted per unit area of the walls. The only force that you can see here is the weight acting downwards. Area of the walls. Area of the wall is, there are two things. This is the outer circle. This is the inner circle. And x is the thickness. Outer circle has a radius r, and the inner one, the gap between them is x. So if I see, I just need the area of the wall, then what do? I subtract the outer area from inner area, which is r minus x, the whole square. So if I expand it, I get W over pi r square minus pi r square plus 2 pi rx plus pi x square. So if you can see here, you can cancel the terms pi r square. And if you can see here, since x is much, much less than r, I can neglect this term. It is already a small term and you're squaring it. It is negligible. So the answer is w over 2 pi rx, which is 8. Now let's see further, investigating the gas laws. See these three containers. In these three containers, you can see that the temperature in the first is least and temperature in the last is the highest. As the temperature increases, the kinetic energy associated with the gas molecules increase too much, where we can very clearly tell that pressure is affected with temperature. Look at the next one. If you can see here, volume is changing and that is affecting the pressure. So comes the first law, which is what we can tell is as the temperature increases, pressure increases, which is P is directly proportional to T. Same thing is applicable to volume. As the volume increases, the temperature also increases. And the last one, we can see that pressure is inversely proportional to volume. That is, higher the volume, less is the pressure. So these are the three gas laws that we are investigating. Now we are going to study about kinetic model of an ideal gas. So ideal gas has certain properties or assumptions, and we need to know these by heart. First postulate is we are considering the ideal gas as perfect spheres. They are perfect spheres and perfectly elastic. That is, after collision with among each other or with the sides of the container, they don't lose kinetic energy. They have no intermolecular forces. This is very important. That is the potential energy of whether you make the bond or break the bond. The intermolecular forces remain same in all the states. The intermolecular forces remain same always. Because the potential energy doesn't change. And the next is the volume of the gas molecule is extremely small as compared to the volume of the container. So these are the 4 or 5 postulates that you need to know. As against this, the ideal or real gases are not perfect spheres. They are neither elastic. They have potential energy associated with them. That is, they have intermolecular forces and the sizes are not small but relatively larger. So these are the comparative properties of real gas and ideal gas. If we look at this question, which assumption is the part of molecular kinetic theory of ideal gas? Molecular kinetic theory of ideal gas tells you that a gas is made up of tiny identical particles which are in constant random motion. So the answer which is correct is C. The system now can see that the piston is pushed inside and there is a gas inside it. As the piston is pushed inside, can you see the temperature of the gas is increasing? So this literally means that when you do work in a given system, that work is associated with change in the kinetic energy of the gas molecules, because when you press in this syringe piston, there is less room for the gas molecules to move around, which reduces the volume and increases the pressure. Pressure increases means the kinetic energy associated with the gas molecules increase, and that results in rise in temperature. As against this, if you do the opposite thing, that is, you allow the piston to come out, you're giving more space to the gas molecules, that is, volume is increasing. That will reduce the pressure or collisions with the sides of the container, and hence the temperature drops. So when you are pushing the piston in, you're doing work inside this gas molecule, so you're doing work on the gas. As against this, if you are taking the piston out, you are allowing it to cool down. So work is done by the gas. So work is done on the gas when volume reduces and pressure increases, and work is done by the gas when it cools down or volume increases and pressure reduces. Let's see one more exam style question. The temperature of an ideal gas is reduced. Which one of the following statements is true? If temperature is reduced, what will happen to the collision? The molecules collide with the walls of the container less frequently, more frequently. Time of contact will be reduced or time of contact will be increased. The answer very clearly tells you the answer is A, because when the temperature is reduced, the collisions that results in rise in pressure with the walls of the container will change, will become lesser. Now, when we join together three different gas laws, which is pressure is inversely proportional to volume, pressure is directly proportional to temperature, volume is directly proportional to temperature. So looking at this, we can very clearly tell that if pressure is inversely proportional to volume, then the product P into V is a constant. This is called as Boyle's law. Same way, if pressure is directly proportional to temperature, then P over T is another constant, and V over T is another constant. So merging all these equations, what can we tell? PV is equal to N is the number of moles, R is the universal gas constant, and T is the temperature. This equation, which merges all the ideal gas equations, is called as the equation of state of an ideal gas, where P is pressure, V is volume, N is number of moles, R is the universal gas constant, and T is temperature. Hello, 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 hello. Hello, hello, hi. So PV is equal to nRT is called as the ideal gas equation, where P is pressure, V is volume, N is the number of moles, R is the universal gas constant, which has a value 8.31. And see the unit, it is joules per mole degree Kelvin. Let's look at a question. The question tells you that ideal gas is kept in a container of a fixed volume. Temperature is 30 degrees Celsius. Pressure is 6 atmosphere. The gas is heated at a constant volume to a temperature of 330 degrees Celsius. So which gas law will you apply here? It's a fixed volume and pressure and temperature. So we are using the equation E is directly proportional to T. So first thing we need to know, this gas law, P1 over T1 is a constant, and that is always equal to the another condition P2 over T. Next thing what you should know is, in all the gas laws, the temperature should be converted to Kelvin. Is plus 270. So try to work out the answer, changing all the temperature to Kelvin and redoing the thing for P2. If we can see here, P1 was 6 over 303 Kelvin is equal to X over 103. So using this, find the value of X. The answer that you should be getting is around 12 atmosphere. The answer that you will be getting is around 12 atmosphere. Let's do another question, which is a theory. The internal volume of a gas. So you are given the volume of a gas, an ideal gas pumped into a cylinder until the pressure becomes 20 megapascal, which is the pressure. The temperature of 17, where you have to remember to add 273, which will be 290 Kelvin. The number of moles of the gas in the cylinder. So you start with PV is equal to NP. Pressure is 20 into 10 to the power 6. Volume is 2 into 10 to the power minus 2. You have to find the number of moles of gas in the cylinder. N is the number of moles. R is 8.31. And T is the temperature in Kelvin, which is 290. On rearranging, we should be getting the answer 170 moles. You can see it clearly. PV is equal to nRT gives you answer for N. Next, find the number of gas atoms in a cylinder. You know the relation is equal to number of gas atoms or the Avogadro's. On rearranging, we get N is N small n times Na, which gives you 1 into 10 to the power 26 atoms. You see here, ideal gas equation is PV is equal to nRT, describes the behavior of an ideal gas, which the equation of state is given, describes the behavior of real gas. Which of the option describes the behavior of a real gas? Only at low pressure, large volumes, or only at high temperature, only at large volumes and large pressures, or at all pressures and volumes? Which equation gives you the property of an ideal gas? They are asking the property of a real gas. So in property of real gas, they have potential energy. So to have potential energy, it should be large volume and low pressure. Which of these equation is the correct equation for P versus T, where T is in degrees Celsius? So pressure of gas at 0 degrees Celsius is not zero. Absolute zero is happening at a temperature where the pressure is the lowest. That temperature is minus 273 degree Kelvin. Sorry, minus 273 degrees Celsius, which is called as 0 Kelvin. At a temperature of 0 Kelvin or minus 273 Celsius, pressure of an ideal gas goes zero. Which of these shows that? Naturally, you have to extend the x-axis and try to extend the graph and see which graph touches with the minus x-axis. Very clearly, you can see that it is only the A graph shows a negative intercept. The x-axis at x is equal to minus 273 degrees Celsius. Get this graph now. It is P versus T. Which of the following is the best interpretation of the intercept and the gradient? So when you extend, where will it meet? See here, tends to meet at 0. And what is the gradient? Gradient is P over T. If I have 1 mole of an ideal gas, means N is 1. Use the ideal gas equation, PV is equal to nRT. Rearrange to have P over V as the subject. N is 1, so equate this as 1. So R over P. P over T, sorry, this was P over T equation. So you have R over V this side. So the gradient of the graph should give you R over V and the intercept should be 0. The option is B. See here. So that's all for today, folks. Let's meet on the second part of gas laws to understand the kinetic theory of ideal gas and solve various exam style questions. Bye-bye.